Okay, and then you're going to ask me some questions on the homework because I even have some things written up on that. Well, some of you know what the factorial is, but I can't assume that you all know what it is. So, first question, what is a sequence? David, what's a sequence? List of numbers. Can't use the word series because now we're going to get, because A2 is a series. So they're going to get all confused. So this is a list of numbers in a definite order. Is that okay, Ori and Eric? What does it mean for a sequence to diverge or to converge? Okay. If you did the homework, you might have some problems that were hard, but yes. No, n is always greater than 0. Well, greater than or equal to 0. Because now you're going to be bothered by that. We're going to do this. We'll do this problem. An integer is the whole number and its opposite. N is going to be what they call a natural number. But it could be 0. So I don't even want to use that. Okay. Would you like to learn how to do this on your calculator? Let's see if I remember. I have a couple calculators here. We have to change our mode. I had a couple. Oh, yeah. So if anybody wants a calculator. You don't have one either? Okay. Who else does not have a calculator? That's it. I don't know where all my calculators are. Now, you could make a list. But let's first look at this. No, we're going to go to sequence mode. And so I'm going to go. Did I close it? I guess I did. Oops. Then Monday, if I get through all this today, then Monday will be question answer work day kind of thing. Pulling it all together. Oh, I have a worksheet for that. You have that worksheet. You do. But I got to get. Okay, so I'm going to quit that and I'm going to go into my mode. Clear. And if you go down here, sequence is right there. And they use these little, I believe they use muse. Instead of n, they're going to say mu. Pretty sure that's what it is. I could be wrong. won't be the first time or the last. Okay, so mode. Okay, we have done some stuff with parametrics. We will do lots of stuff with polars. That's where you get the pretty pictures of the polars. And then the sequences, which look kind of weird. They look very weird. And now, press y equals. Oh, it's u's. Instead of a of n, they're using u of n. They're starting with 1. Okay, Matt? I want to start here, and I'm going to type that in, so I want n factorial. So guess what? You have an n right there. So it's n, and I have to talk about what a factorial is. And does anybody know where the factorial is? It's under math. And I got to go all the way over to probability. Everybody with me? 4. Then we're going to divide by, is that n to the n? Whoa. N to the n. The question I had for you is, which one do you think is stronger? Do you know what n factorial is? Okay. Well, let's start with 3 factorial means 3 times 2 times 1. And so 8 factorial would be 8 times 7 times 6 times 5. Let's see if I can count backwards. So what's n factorial? So it's n times n minus 1, n minus 2, n minus 3, 3, 2, 1. Have you done this in stats? because it always ends with 3, 2, 1. It's all the numbers that you multiply by the first number, 1 through n, but this is 1 less than that, it's 2 less than. Okay, so you're going to have to know that. You might. I'm assuming you don't. That's okay. It's better to make that assumption. So which one do you think is stronger? N factorial or n to the n? Well, let's find out. We'll graph it. Because if n to the n is stronger, that'll go to 0. Now, can I make this a function? No. What's f of x? X factorial? No, can't do it. Okay. So that's the problem. The factorials are always going to give us a problem. And exponentials of exponentials are going to give us a problem. Okay, now we are going to go into our window. Okay, I'm going to go back down here. We always start with 1. You could start at 0, but why can't I start with 0? Because I can't do 0 to the 0. That's one problem. And I can't divide by 0 either. Now, 0 factorial will be defined to be 1, and I'll write that in a second. Okay, so you have this one, and then you put in your sequence. Now, we got to get our window. And how many elements do you want? How big do you want n to go to? I've got 10 on this. 10 is going to get really small fast. No, but think about that. You're going to do 10 factorial divided by 10 to the 10th. That's huge, right? Okay, and it's I think you just leave your plot start at 1. Plot step is 1. And now, will these ever be negative? No. So we'll start with x min as 0. And 4.7 will be fine. It doesn't take long for this to converge. And is it always going to be positive, the y's? Yes. What's the biggest number that's going to start with? 1. Because n is 1. Then when you get 2 factorial, you're going to get 2 over 4. So it's going to start. We could start with that. I'm not going to get any bigger than 1, so why don't we put a max of 1? Okay, ready to press graph? Now, why is it connected? Oh, it shouldn't be connected. Let's change this to dots. I'm going to go, oops, press that to get dots. There it is. Oh, you only have 3 choices here. Now, 83s, I think it's going to be dot automatically. That's why I was surprised when I saw it connected. Yeah, unless you have the new operating system. Now, see, there it is. Does it converge to 0? Yeah. Yes, but can we show it's convergent? So some of the homework problems are like this. They're hard. Okay, we are going to use the squeeze theorem to do this. Oh, and let me write this down. And this is by definition. We will not have imaginary numbers. If you get imaginary numbers in the exam, like some people did last year, then they did something wrong. There are no imaginary numbers in calculus. By definition, 0 factorial will be 1. It works out nicely for us, and so somebody made that choice. Chaos? So how are we going to do this? A sub n is equal to n factorial over n to the n. I'll be honest. I didn't have time to review this. So I'm just going to model what I do. When you get to these problems, it's kind of hard. I want to be able to compare it to something with the squeeze theorem. Maybe you can guess, maybe you can't. But I want to look at that. So let's first start by listing out some of the elements of the sequence, because it gets to be a little easier when you do that. Well, a sub 1 is 1 factorial over 1 to the 1. We're going to use the squeeze theorem. Those should be the hard problems for you, when you have to use the squeeze theorem. Because 1 factorial is 1. Yeah, let's write our number of terms. Because then you'll see, at least, if I don't know what to do, that's what I'm going to do. So it's 2 factorial over 2 squared. Well, you know, I'm going to write it like this. 2 times 1 over 2 times 2. Because I'm looking for patterns. And you know, honestly, that's what math is. It's all about patterns. So A3 is 3 factorial over 3 to the third. Well, that's this. 3 times 2 times 1 over 3 times 3 times 3. You know, but forget that. There's another pattern. Let's do the fourth one. A4 is 4 factorial over 4 to the fourth. So I'm going to have 4 fours there now. So 4 times 3 times 2 times 1 over 4 times 4 times 4 times 4. Okay with that? Notice that what happens with the first factors, they are what? They're 1, right? What about this number? That's 1/2. This is what, 2/9. This is 6 over 64. What's true about all those numbers? They are less than 1. So when I multiply all that out, it's always less than 1. Okay. Can we try the nth one? Because that's where it gets tricky. Okay. So a sub n is equal to n factorial over n to the n. Okay, so it's n times n minus 1, n minus 2, 3, 2, 1. And then I'm going to have n of the n's. Well, have you noticed that if it was 4, I had 4 terms, 4 factors there? So I'll have n factors. But these are equal. The numerator and denominator have the same number of factors. So it's n times n times n and n and n. Okay. And now I'm looking for patterns. Well, this is 1, right? That's 1. And if I take all of these, how do they compare to 1? Well, look what we just did. Even if I don't take this. Let's just take this guy. How does that compare to 1? It's less than 1, right? It's less than 1. So if I take 1 times this number, which is always less than 1, times 1 over n, how does that compare to 1 over n? It's less than or equal to that, right? This one said I wanted to figure out what to compare it to. These numbers in here will always be less than 1. And you're right, I could put 1 over n in there, but then I don't know what to see to compare it to. And I want to compare it to this because guess what? This is still greater than or equal to what value? They're all positive numbers. 0. We'll use the squeeze theorem. Let's take the limit and let n go to infinity. That's still 0, right? Okay, Ori? And this is less than 1 over n. So if I do the limit of this as n goes to infinity, there's no other way to do this. And limit as n goes to infinity, what's this one? 1 over a big number is 0. So what has to happen with all of that? Has to be equal to 0 by the squeeze theorem. That's the reason why we do the squeeze theorem way back and wherever we did that, I don't remember. Yes. It's hard. N goes to infinity. N goes to infinity. N goes to infinity. N starts at 1 and goes to infinity. Okay. No, because the first term is, but remember, I'm looking at the sequence. I'm squeezing it between 0 and 1 over n. Okay. Because do you believe that this is smaller than 1? Some of you may have seen it right away, that it was smaller than that. But this is, I would have to do proof by induction to actually prove that this is less than that. Not really doing that. It's not really, it's a good show that, but it's not really a good proof.
Wait, so how do you get like the 0?
Because n is always greater than 0. We're not going to do negative numbers. So it's trapped between 0 and 1 over n.
The 1 over n.
I had to write out enough of these to see that this is 1 over n. There's n. This is 1 over n. So 1/4 is 1 over n. So this is clearly less than 1/4. This is clearly less than 1/3. Less than 1/2. So if I go back, should we graph? Let's take my graphing calculator and let's graph the other one. But I'm going to leave it connected, I think. So now I'm going to go to my other one. Let's put this one here. We'll start at 1. And let's just do 1 over n. Do you believe it's less than 1 over n? You just believe me blindly. Okay. Now that's connected, so you can see that, because otherwise you won't be able to see it. See, these are the dots from the sequence. This is bigger than that. And if I want to change my x values to be bigger, let's make the x's go to 10. Yes. So I had the original sequence, and then I had 1 over n. Now, will anything be this hard on the exam? No, but are you expected to know this at the college level? Yes. 0. Because our terms are always positive. N is positive, right? Notice n started at 1. Okay, let's look at the graph again. There it is. But you can't even see those dots. If I do a trace, okay, here I'm in my little sequence. Okay, guys, there it is. I'm going to trace it again. There it jumps down there. And watch what happens. I'm going to get really close to that axis. There it is. Clearly, it's less than 1 over n. And we know 1 over n goes to 0. Trap below by 0. What has to be true then about this weird sequence? It's got to go to 0. And there's no other way to do it algebraically, because it has that factorial in it. And then it has an n to the n besides. So you have a problem that asks you to do this. Will I test you on it? No, but I just think it's very cool to see that. Now you see where the squeeze theorem comes in handy. It will come in handy throughout this chapter. There'll be other things we're going to have to use the squeeze theorem. Okay. This is another really important sequence. Now, I got too many letters there. The question is, what values of R is this sequence convergent? So you know what? I'm going to do exactly what I did before. I'm going to do trial and error. To see what's going to happen, I'm going to do guess and check.
On every test, you always say no points for guess and check. Yeah, so
that's not what you're doing here. It's a different kind of problem.
It's also hypocritical how AP exam you don't have to simplify, yet we lost points in the last exam.
Oh, no. That wasn't the problem. Okay. What would you now? The variable is the n. That's what you're going to be leaving just as an n, as a variable. I want to know what constants can I put in for r so that my sequence will converge. So if I said r is equal to 2, this is going to be real important in section 3, I think. If r is equal to 2, I get 2 to the n. Does that converge? Well, what's that sequence looks like? It looks like 2 to, let's start with n equal to 1. 2, 4, 8. Okay, does that converge? No. What's another significant number you think might converge, or might be looking at something? Well, what about 1? Well, what's 1 to the n? What does that sequence look like? Yeah, this is hard, because you're not used to thinking this way. So it's 1, 1, 1. Does that converge? Yes. Does it converge to? 1. It's always 1. Oh, it does lead to a lot of excitement. No, it's always 1. Yeah, this is going to be 2 cubed, 2 to the 4th is 16. So it's infinity, so it's divergent. Okay, you guys ever hear of chaos theory?
I've got a chaos program.
Now, we could do that. We could do chaos theory after the exam, but this is related to chaos theory. We get chaos when we have a border where the results vary significantly at that place. So if you put in r equals 1.001, what is that going to give you? Well, it's 1.001, and then you square it. Am I going to be bigger than 1? And then you square it again, it's going to still be bigger? So this is going to be growing to infinity. Well, at 1, this is called a fixed point. You don't have to know that, but that's what it's called. You're fixed at 1. If you're a little bit bigger than 1, this is going to go off to infinity. So you've seen the pictures of the Julia sets, the colors, the beautiful color pictures, and I don't have any of my pictures up here. I could put it on my iPad and show you that way. Oh, you can. But this is going to take a while to get to infinity if you were to time it. How about that one? That goes to infinity really fast, doesn't it? So that would be colored purple. And this is all random. The guy who decided to do this said, I'll just color that purple. If they're really slow, I believe they're like orange or yellow. So this would be colored yellow. And if you were to graph this in a coordinate plane, and I have more than this, you would get, and you get patterns, amazing patterns. And so I could, if during work time today, if we get there, I'll bring up my Julia sets on my iPad. There's a lot of applications. They can find breast cancer using chaos theory. There are pipelines in Texas where there was a break in the pipeline, and they did not want to dig all the pipeline up to find the break. And they used chaos theory to find it, and they did find it. I know it sounds like it's chaotic, but it's not. That's what chaos theory is about. Um, no, n is it starts at 1. We'll start at 1. You could do 0. Can be negative. Oh, well, what if R is, well, let's look at, see if we have some chaotic behavior. What's this one going to do? This one's going to go to 0. Okay, so this is what we mean by chaos. This is going to go to 0. When you are really close, at 1 you're fixed. But if you're just, I don't care how much bigger than 1 you are, just a teeny tiny bit. It could be a million zeros and then a 1. That's still going to go off to infinity. And if you're really close to 1 from the other side, 0.9, you can have a million 9s there. It will go slow, but and we're going to color ones that go to 0, we'll color them black. And that's going to go to 0. So this is the border between this behavior and this behavior. Yes, it's still convergent. Still goes to a number. And that's the boundary. That's what you call the boundary. And so anything inside here, well, it's going to be a circle, actually, kind of. So what about r equal to 0? Goes to 0. Okay, what do you think about all the values between 1 and negative 1? It's going to go to what? 0. In fact, we included 1. What about negative 1? Do we get to include negative 1? And we did that yesterday. Whoops. Okay, so negative 1 to the n does this. It goes negative 1, 1, negative 1, 1, and that's called a periodic point, but it doesn't have a limiting value. So we cannot include that. And what if you do r equal to negative 2? Then that's going to look like this. Negative 2 to the n, which is negative 2, 4, negative 8, 16. Guess what? That diverges as well. And that clearly diverges. Part of it's going to positive infinity, part of it's going to negative. So the r values where this will converge, and this is going to be important throughout this chapter, is r is going to be less than or equal to 1 and greater than negative 1. Now, if you want a little bit more about the chaos theory, what happened? Well, Francois Julia, which was back in the 1900s, was the first guy that actually got credit for it. But Lorentz, he was a very strange mathematician, and he was kind of crazy. And I have a former student who's kind of crazy, too. He did 2 things. He did a whole bunch of stuff, but he did 2 things that I can remember. And one was he decided to change the number of hours in a day to 36 instead of 24. So that means, because he thought it'd be interesting, what happens? But what happens to your night and day? It gets all mixed up. Okay, that just shows you've got a crazy guy. It didn't last very long before he said, can't do that. We got to stick with the 24-hour day. Kind of interesting. I suppose you could change how we divide up minutes and stuff. You could do that. But then the other thing he did is he built this water wheel. And in this water wheel, and my former student, who's an engineer, and actually he has made some of the chips for the iPod, the iPad. It's out in California. Anyway, he had nothing to do. It was in Texas. There's nothing to do in Texas. So he built a water wheel, and on these water wheels, you put these cups, and water's going in, but at the same time, there's holes. Now, you would think that this thing would either just spin around when you put the water in, or it would all leak out and it would just not do anything. But what happens is, if you get the right balance, you get chaotic behavior. And I used to have a video of his water wheel, and I don't know whatever happened to it, which is unfortunate. But what happens is it might do this, and then it'll stop, and then it'll come back and maybe go around and around, and then it'll stop and come back, and it just keeps going. And it's chaotic. You can't make predictions for it. He just wanted to see it because he had read about the Lorentzian water wheel, and that's chaotic behavior. Pardon? So you got water going in and water coming out, and it took him a while to get it balanced so that you would get this random chaotic behavior. Well, remember Lorentz? He wanted to change the number of hours in the day. There's something else he did. He did the wet, and here's how he really found the chaotic behavior. He was running a big program because this was back in the 60s. We had these big computers. They would take up this whole room. What you guys have in your little Mac would take up this whole room. You have no idea what that was like. But anyway, he's running this program, and it was weather. And he says, and he would always run out of time with this program. He says, you know what, tomorrow I'm just going to come in and start where I left off. And he did, and he got dramatically different results. It's that difference between one being a little bit bigger than one and a little bit less than one. And I can give you more functions, really crazy things that you can see that you'll find these places where the behavior is different on one side than it is on the other. And we aren't going to worry about it in this class, but it is something you have to worry about when we do our convergence test. If you were a mathematician, you would have to worry about it. Yeah, and the butterfly effect is related to chaos theory. Read Jurassic Park. Do you think it matters? If you're doing a random drawing and you put your name in or you don't put your name in, have you changed the outcome? Yeah. Even though you're not probably going to win, you still change the outcome of who does win. This is kind of an interesting thing. A lot of things you can find out, but this is another branch of mathematics. It's the newest branch of mathematics. You got to go to Boston University if you want to study this. I mean, because you study with the Bob Devaney, who I know actually. And he came and did this at the University of Minnesota. That's how I learned about it. But it's way back in the 80s, which for you is a long time ago. For me, it doesn't feel that long. But it was the newest thing out there. Okay. This is just a definition. And the word is monotonic. You know, I never use the crayons. Monotonic. Single. Monotonic means your function's always increasing or always decreasing. Now, do you remember how to show a function's increasing or decreasing using calculus? So if it's increasing if f prime is greater than 0, and it's decreasing if f prime is less than 0. Okay. So an increasing sequence means it's just going to keep growing. Decreasing will go down like that. We're going to be formal in this section, but after this, you're just going to look at your sequences. You're going to be able to say, oh, it's decreasing. You're not ever going to have to prove it on the AP exam. It's nice to have been through this because I know these things now. So I want to show that that sequence is increasing or decreasing. I'm going to use calculus because I can do it, right? What would my function be? If I had a factorial in there, I'd be in trouble. Now, do you guys think it's increasing or decreasing as n gets bigger?
Increasing.
Right. So that's all you have to do on the exam. But if they asked you to show it was increasing or decreasing, I would get a function here and then find the what? The derivative. How did I do that? Find the derivative. Do you want to use the quotient rule, or do you want to rewrite it as 3 times x plus 5 to the negative 1? I like that. So what's f prime? So I'm not too worried about this. I want you to recognize more if it's increasing or decreasing. But it's negative 3, x plus 5 to the negative 2. Now I better change that so I can interpret that. So that's negative 3, and that's x plus 5 squared. Well, clearly that's always positive, so this is always negative, right? So that's a proof. Another way to prove it is to see how this compares to 3 over n plus 1 plus 5. Is that getting smaller when I added another number there? Now you got to think a little bit, because this would be 3 over n plus 5. That doesn't change, but this is 3 over n plus 6. So now you've increased your denominator just a little bit. So does the fraction get bigger or smaller? Yes, you do know. You have to think. That's all. But they're not going to trick you. Matter of fact, last year they were so obvious, they even said it was a decreasing sequence. Still, students missed it. I couldn't believe it, but they said it's decreasing. You'll see the theorem later on. Okay. Don't worry about that if you find this stuff hard, because all you're going to have to do is look at it and say it's decreasing. Show that that's decreasing. I could do a derivative.
Wait, what's that?
You could do that. I'm not going to worry about it because it's just not worth our time. Do you believe that's decreasing?
Yeah.
You know, and if you put some numbers in, you can see it's decreasing. That's good enough for me. Otherwise, you put in n plus 1, and you put in n plus 1 here. And then you have to cross multiply. They're not going to give you that, so I'm not going to worry about it. Okay. Couple sequences to look at, because when you look at that, it's kind of scary looking. I think this is our last slide. Yeah, but there's, look at them though. Look at all these. Oh, maybe I've been doing that better. Oh no, that means such that. Okay, math people invent their own language. That means such that. This is all math language. If you start getting it, you go into math as a major. If you want to be a teacher, you have to do this. It's only a couple classes that's this bad. If you get through them, I got through them. That means for all. Aren't math people weird? We're so lazy, we don't want to write all the words out, so we made symbols. So it's a language. Okay. This sequence is n, and we know where that looks like. That at 1 we're here, at 2 this is bounded below. It's always positive. Okay? This one is bounded above because what's the limiting value of this? As n goes to infinity, this is no bounded, right? What's this limiting value? As n gets really big, remember you can look at it as x over x plus 1. Well, think about it. Does the 1 matter? No. So this looks like 1. So it's a bounded above by 1 and below by 0. And you're not going to worry about this there, but I'm going to present it anyway. A sequence is bounded above if there's a number such that it has a maximum value here, the limiting value. That's what that means. It just means this is this bounded? Is there a limiting value there? No. But it's never going to be below 0. It's never going to be below 0 in Shanghai. No, it's just a statement. Now, you don't have to know what, you just have to know what it says. A sequence is bounded below if there's a number that it's limited by on the bottom. So you could actually have a sequence that does this. Could do that, right? It's bounded above and it's bounded below. Can you think of a function that's bounded? Easy function, trig one. That's not trig. How about the sine of x? It's always between what two values? So it's bounded below by -1, is above by 1. Now, that does not converge if x goes to infinity. But if this would always be decreasing or always increasing and bounded, then it would converge. But you're not going to run into that, so I'm not going to worry about it either. But that's what this says. Not every bounded sequence converges. This is clearly bounded. Not every monotonic sequence is convergent. This is monotonic too, because n is always increasing, right? You have to have both. But if you bound your sequence and it's always increasing or always decreasing, it will converge. But you're not gonna see too much of that. Okay. That is it. That's really all the rest of 8.1. So questions on the homework for 8-1. There's a hand already. And then Monday, I'll give you a worksheet with a bunch of sequences on it for you to decide. And what you do is you just write out the terms if you need to. Okay. So we're going to look at 8-1. What time is it? Yes. Whose phone? Yeah, these are not easy. Point in. Okay. Okay, guys, turn that off, please. Thank you. Now let's change this to a function. Yes. Homework. We did 1 through 16. Now you have to look at the assignment sheet for the rest. You know, and you have a little time, but we will start section 8-2. Sorry, I said Wednesday, but Tuesday we will start it. Well, you guys, this question. If I rewrite this as this question, is it easier? I want to take the limit as x goes to infinity of this. That's okay, because when I looked at it with the ends too, I go, oh, that's kind of hard. Because when x goes to infinity, this doesn't count for anything. So it looks like 5x squared over x squared, which is 5. Yeah. Because if you want me to do it formally, I can divide by x squared. Okay, guys. 3 over x squared plus 5. And then this is 1 over x plus 1. And these are going to go to 0. That's how you would formally prove it. But you don't have to do that. Your Eric's SOB method is only works for polynomials. And you will be in trouble. Yes. Probably. Can you figure out what this sequence is? Well, look at this. This is one. Well, first off, it's an alternating sign. Remember how to write those? Now, okay, this is 1, 2, 4, 8. What is this going to be? It's 2 to the what? N. I don't care if is that going to start out right? N is equal to 1. I'm going to start with a negative. So guess what we have to do here? N plus 1. And this is 3 to the N, right? I think so. So that this is this. So it's negative 1 to the N plus 1, which I don't really care about, but it's 2/3. Now, we just did this problem. That's the R to the N. Is that going to converge? 2/3. Remember, if this is that R problem. If R is between 1 and negative 1, it converges to 0. Don't forget the theorem that talks about the absolute value of this. And it says if this converges, the absolute value of that, which is 2/3 to the N, then the original one that's alternating sign also converges, even if it's not alternating. Doesn't matter. Converges to 0. Well, I tried N, and then if I used N equal to 1, it became a negative. Oh, wait, maybe I'm wrong. Oh, N equal to 0. No, I'm wrong. I want just N, but it doesn't matter. It just alternates the sign. No, if N is equal to 1, then this is 2/3. Or I can start with 0. If N equals 0, then this is 2/3 to the 0. N equals 1, then I get a negative, and I get a 2/3. It doesn't matter. I don't really care about the end behavior. Yes. Okay. Shh. Okay, guys, I need quiet. I just want to know. It asked you to find this. It says find the general term for it, and then it says does it converge? I can't teach you that. You have to look at it. And I saw 1, 2, 4, 8. Next one's going to be 16. I'm looking for patterns. I guessed it was 2 to the nth. Sometimes it's very hard to find that general term. So I'm not sure how to do 10 to find that general term. I'm more interested in whether or not it converges. It doesn't matter. No, but we'll get into more about the ends. They're counters. They started with n equal to 1. I started with n equal to 0. So if I want to start with n equal to 1, I have to get my first term has to be a positive 1. So I have to subtract 1 to get that positive, and 2/3. I write it as 2/3. You want to write it that way. N minus 1. So if I put in 1, then that's 2/3 to the 0. It's the same thing. It's just your starting value. Now, I don't know what they do for 10. I just know it doesn't converge. Did anybody find an answer for this? How about that one? Does that converge? No. How can you describe that? Oh, I did. Oh, that was not very nice. What? Guys, it's divergent, but can I write this with n's? What's halfway between 5 and 1? 3. So if I do 3 to the n plus a negative 1, 2? No, I don't want to do that. I want to do this. Plus a negative 1 to the n times 2. So let's say n is equal to 1. Then that's 3 plus a negative minus 2, which is 1. Well, we'll fix the n's to the starting values. If we start at 0, I think we're going to be okay. No, we're not going to start. We can't. Yeah. No, that won't work. We have to start with n equal to 1. Now, but let's just play with it. N equal 2. So it's 3 squared. Oh, maybe I do want the 2 in the n. Oh, no, I don't want the n. Thank you. Yeah, then it works. Then this is going to be plus 2, which gives me 5. Now, this started with 5, so guess what I have to do? Either n minus 1 or n plus 1. And then it'll work. It doesn't matter. It really doesn't matter. No, it's hard. You'll do that in FST. What's another good one? Did you get number 8? How about 16? Did you get 16? Yeah, let's do 16. And we'll take time next week to look at your test, because I want to go over it, but then we'll see. Okay, 16. Ori, if you're not doing your homework, you need to do it. It doesn't take very long. Because you should have a paper out and you're doing this with me. Okay. It really doesn't take very long. It says determine whether this. That's why I said this is hard. Okay, you guys. Well, we got 10 more minutes of class. Oh no, 5. Well, actually 8. If you want to be particular about it. Okay. Okay, Ori, you get to pick that up. I saw it. And guess what? That's on the video forever. Okay. Now, here you pay attention because you have to be able to deal with these exponents. I am. Okay, so this is 3 to the n times 3 squared. Okay, Eric, what are you going to do when we're going to run into this one all over again. Matt? Drew? And this is 5 to the n. Okay, is that okay? Well, that is 9 times 3 to the n over 5 to the n. That's my sequence. So that's 9 times what? Can I write this as a single fraction? 3/5. You're going to have to be able to do this.
Oh, the principles of exponents student power. Remember that? Seventh grade, Miss William.
Oh, man, you have Miss Williams in seventh grade. Weirdo.
Okay. Now, I don't care about the 9. 9 times a convergent number is a number. 9 times infinity is infinity. All I really want to focus on is this part right here. Now remember, that's my r value. Remember, r to the n is r between 1 and -1. So this goes to what? 0. And you have to be able to do this. 3/5. If you were to write them out, and if you don't know, write them out. So I don't care about the 9. 3/5, what's the next one? Good. What's the next one? Squared. Cubed. Okay, Eric? Is that going to 0?
Yeah, it is. Because
Don't need a squeeze term. Because my r's are in here. We know it always goes to 0. Now, when I take 9 times that, it doesn't matter. What's 9 times 0? 0. So it doesn't matter. So you can ignore those constants. But the trick on this one was to rewrite it. Now we didn't do 8. We did 11, 9, 10. We've done a large part of it, and that didn't take very long either, by the way, of the assignment. The hardest part is to find the general term. But you never, well, I can't say you never have to, but yes, you do have to do it. Okay, now when you get to the next problems, you're going to find them hard. When you get to the, like 34, that's like what I did in class today. When in doubt, list out the terms to see what happens. If you look ahead at them, they're all different. So 29 is a factorial. List it out. Start with n equal to 1, 2, 3, and write it out. You'll see what happens. I promise. Any other ones that you want me to do? I should be recording.